is the second property of the norm. The third one is called the triangle inequality, which says that x plus y less than x plus y. This is called triangle inequality. Okay, so these three statements are the basic property of the norm. The proof is straightforward. For example, we prove the third one, which will use the Cauchy Schwarz. For the triangle inequality, we take the square of both sides and compute x plus y norm square, which is x plus y. Then by the property of the scalar product, the right hand side equals xx plus 2xy plus yy. This is by the Cauchy Schwarz inequality, this will less than or equal to the norm of x times the norm of y. So the right hand side will not greater than the norm of x squared plus the norm of x and y plus the norm of y squared, which is exactly norm of x plus norm of y squared. So from this we immediately obtain the triangle inequality. Okay. Having obtained the basic property of norm, we can now define the distance between 2 points in Rm. Distance. This is the definition. For x, y in Rm, we denote this by dxy for distance. X minus y. The distance between x and y is the norm of x minus y. Is distance between x and y. Why we call this distance? Using the property of the norm, we have this proposition. Firstly, dxy for xy in Rm, dxy is always non-negative, and dxy is 0 if and only if x equals y. Secondly, dxy equals dyx. And thirdly, dxy will not greater than dxz for the third point plus dzy. So because of these three properties, the distance we defined is consistent with our common sense for distance in our real life. So this is justified to call this the distance between x and y. Now the proof of this proposition is very easy. There are easy consequences of the property of norms. For example, we prove the third one. The third one is also called triangle inequality. Okay, we prove this. Now, dxy by definition is the norm of x minus y, but we can write x minus y as x minus z plus z minus y. Now we apply the triangle inequality for norm. We will have x minus z plus z minus y. This is exactly dxz plus dzy. And the triangle inequality for distance is proved. Okay. Using the distance, we can define some special and important subset of Rn. For example, suppose A is a point in Rn and R is a positive number. Okay, then this subset of Rn, which consists of all x in Rn, so that the distance of x to A is less than R. What's this? Geometrically, this is here is our A, and this consists of all x distance. The distance from x to A is less than R. This is a ball centered at A with radius R. So it's a ball centered at A which radius R. So this is a ball. Balls are a kind of important subset of Rn. They are very useful. Another class of subset is called bounded subset. Suppose S is a subset of Rn. If there exists R positive such that S is contained in this ball, centering at the origin, also with radius R, then we say that S is bounded subset. This condition, S contained in this ball, what this means? This means for any x in S, because x in this ball, the distance between x and the origin is less than R. So the norm of x, which is x minus the origin, is less than R. So this is a bounded subset. Okay. Because this kind of ball centering on the origin are very useful, we use a more simple notation. BR is BR 0. So if the center of the ball is the origin, we will delete the center. Just denote this by BR. Indicating its radius is enough. Okay. Now we will go back to the Cauchy Schwarz inequality. It says that x and y, the absolute value of their inner product or scalar product is not greater than the production of their norm. Okay, so if x and y is not 0, we will have xy, the absolute value of this fraction will be not greater than 1. So we have a unique theta. This theta is unique in this interval 0 to pi, such that cosine theta equal xy. There is only one theta satisfies this equation. This theta is called the angle between x and y. So we define the angle using the scalar product. We can do this because we have the Cauchy Schwarz inequality. Okay. Now geometrically, we can this is our coordinate system. This is x1, this is xn. So x is here and the y is here. So we can identify the point x which the arrow from the origin to this point. That is vectors. We can identify the point in Rn which acts vectors from the origin to that point. Okay. Then the theta is the theta we defined is the angle between these two arrows. So this is quite geometric. And a special case is when theta equal to 90 degrees. If theta is pi over 2, 90 degrees, that is to say the inner product of x and y is 0. Then we say that x is x and y are orthogonal, denoted by using this notation. We use this notation to indicate that x and y are orthogonal. Okay, this is our first lecture. Thank you.